Alright, Math 111, Section 5.6, Factoring Trinomials. Let's jump right in. Now that we're expert in Factoring GCF expressions, as in Section 5.5, we're ready to go on to Section 5.6. If I ask you to factor an expression like this, x squared plus 11x plus 24. Alright, well, it turns out if you're given a trinomial expression, often but not always you can factor this. In other words, break this down as a product of two binomials. Alright, what I'm going to do is let's assume that we can do this. If I want my two binomials to multiply to x squared plus 11x plus 24, I'm going to claim that I can choose my first terms to be x in the two binomials, because x times x is indeed x squared. Let's see. We want the last product to be a 24. Now what I'll want here is factors of 24 that add up to 11, because my inner and outer products have to add up to an 11x. So the real core of the problem here is to adjust so I get the correct inner and outer sum to add up to that second term in the trinomial that I'm given. I think I can see it here. Here's a little tip. If this last sign is positive, these signs here must be the same, either plus plus or minus minus. If this given sign here is positive, that means those two terms in those binomials must both be positive. So a little trick might help us to reduce some silly possibilities. Factors of 24. Well, there's a lot of factors of 24. There's 24 and 1, 12 and 2, 8 and 3, 6 and 4, and only one of these layouts is going to work. Well, the idea is through a trial and error process. I think we can all see what's going to happen here. I think 8 and 3 will work. Right? If I check my answer with I can really just check this in my head. X times x is x squared. That works fine. The last product, 8 times 3, is positive 24. That works fine. And the outer and inner product, 3x and 8x, do indeed add up to 11x, positive 11x. So if I start out with this expression, x squared plus 11x plus 24, and I ask you to factor it, I'll return x plus 8 times x plus 3. Okay? And multiplication is commutative, so I can really arrange these polynomials in any way I like. And that's of course equivalent to x plus 3 times x plus 8. So the answer is unique, at least with regard to reordering of the polynomial factors, reordering of the binomial factors. Let's try another one. Factor c squared minus 24c plus 44. Alright, I'm asked to factor this trinomial, and I suspect it can break down as a product of two binomials. Well, the idea here is, again, if it's going to break down as a product of two binomials, I would probably want to pick c in each of the first slots. Notice this sign is positive, which means the middle signs here must be the same. This sign is negative, which means they must be the same negative. So right away I know from that little shortcut that my final answer is going to look like c minus something times c minus something. I'll need factors of 42 in my last slots. So 44, let's see, let me restate that. I need factors of 44 in my last slots. Alright, now 44 has got a lot of possibilities, but I think we can all see that 44 is 2 times 22, and that this outer and inner product will add up to a minus 24c. So through a trial and error process, I get a final factored form of c minus 22 times c minus 2. Okay? Up the ladder we go. Factor 5x squared plus 7x plus 2. Well, the bad news here is I don't have a lead coefficient of 1. It's always easier to factor a trinomial expression like this when you've got a lead coefficient of 1. Well, the good news is 5 is prime, so really I've only got one possibility for my first slot, namely 5x and x. Alright, the same rule previously discussed holds true. If this last term is positive, the signs in between must be the same, either plus plus or minus minus. If this middle term is also positive, well, then I know they must be positive. So I can kind of eliminate some possibilities right off the bat. 2 is, of course, 2 times 1, and there's only really one way to break down 2 and 1. Well, I can put 2 and 1, or 1 and 2, and only one of these layouts is going to work. If I try 2 and 1, let's try it. 5x, my outer product will be 5x plus 2x is 7x, and that indeed does work. So once you've found a factoring that works, you can stop searching. Again, the answer to each of these factoring problems is unique, at least allowing to, with regard to reordering of the factors. Alright, so 5x plus 2 times x plus 1, let me check it. 5x squared is the first product, 5x and 2x is the outer and inner sum, adds up to a 7x, and 2 times 1 is 2, positive 2 is the last product. Okay? Let's try another one. 3p squared minus 4p minus 4. Okay. Again, 3 is prime, so if it works, I'm going to need something like this. 3p and p in the first slots. Now, if this sign is negative, that means either I'm going to have a plus and minus, or a minus and plus. That means the signs in between these two binomial expressions are going to be different. And which one? Well, you have to determine it by kind of a trial and error process. I think I see what's happening here. If I try a 2 and 2 in the last slots, again, I'm just speculating here, my outer product will be a 6p, my inner product will be a 2p, and I think I can play around with the signs of 6p and 2p to add up to a minus 4p. If the sign here is negative and the sign here is positive. Alright? So my first product is fine, 3p squared. The outer product, minus 6p plus 2p is minus 4p. That checks out. And the last product here, minus 4, that works too. So when I ask you to factor 3p squared minus 4p minus 4, using trial and error and maybe a little hard-won finesse, by practicing these things, I get 3p plus 2 times p minus 2. Okay? On we go. Well, I kind of left the possibility that some of these just won't break down. And let me give you an example of that. If I ask you to factor this expression, well, again, we can kind of narrow down our possibilities here. 7z squared, 7 is prime, so I'm going to have 7z and z in the first slots. This last sign is positive, means the signs in between must be the same. This second sign here is also positive. That means these signs must both be positive. And 2 and 1. Well, 2 only breaks down two different ways. 2 and 1, or 1 and 2. And I don't think any of these possibilities work. Let's check it. If I'll try this first possibility, the first layer here. 7z plus 2z gives me 9z. Well, that's not going to work. How about the bottom layout here? I'll get 14z plus 1z. That's 15z. That means that layout's not going to work either. And those are my only two possibilities for this problem. And if they both don't work, well, then I conclude my polynomial is prime. That means it cannot be broken down into a product of two simpler polynomials. Just like a prime number can't be broken down into a product of two lesser numbers, same with a prime polynomial. Prime polynomials cannot be broken down into products of simpler polynomials. Let's try another one. Factor 6z squared plus 17z plus 12. Alright, now I get a little itchy here when I see 6. 6 has got more than one possible layout for that first slot. Let's see what I'm up against here. I can either have 6z and z in the first choice here, or 3z and 2z. Now, as we said before, if this sign is positive, the signs in between must be the same. If this sign is also positive, that must be that they're both the same, positive. Alright, now I've got lots of possibilities for 12 here. I've got 12 and 1, or 1 and 12. 6 and 2, or 2 and 6. And 4 and 3, or 3 and 4. Now, only one of these layouts is going to work. So basically, I've got lots of choices here. Now, I think I see it here. I'm not sure if you see it. I can't fit this all on one screen. Let me try this again. I'll write this again. 6z squared plus 17z plus 12. And if I ask you to factor this, I'm going to try to factor this as a product of two binomials. Alright. I think I see, let's see. If I pick 3z and 2z in the first slots, I know both these signs have to be positive. I need factors of 12 here. I think I see it here. If I can have 2z, if I put in a 4 and a 3 in these slots respectively, let me check. Again, the real battle here is to get the outer and inner products to add up to the second term in the original polynomial statement. Let's check it. I'll get a 9 for my outer product. I get a 9z. For the inner product, I get a 8z, and I do see that the outer and inner sum is indeed 17z. I know the first products are okay, 6z squared, and I know the last products are okay because I only considered factors of 12 in those last slots. Alright, so let me clean that up. Oops. 6z squared plus 17z, should have had a z there instead of an x, please forgive me, probably knew that anyway, plus 12 is equal to 3z plus 4 times 2z plus 3. Okay. Alright, let's go on to the next problem. How about something like this? Yeah, they get a little nastier. Alright, how about if I ask you to factor something like this? Well, all the previous examples have been degree 2 trinomials, and this is a degree 4 trinomial, isn't it? Well, I claim we can use the same principle. First thing I'm going to do is arrange it in what I call standard form. Basically arrange my terms in decreasing degree. Well, if I do that, I'll put the fourth degree term first, and then as long as I tag that negative sign along with the t squared, I can put the degree 2 term in the middle and the degree 0 term with a constant in the last term. Now notice, this middle term is degree 2, this first term is degree 4. I think you can see if I split up my first product as t squared times t squared, then the inner and outer products will be multiples of t squared. This sign is positive, means again these signs are the same. This sign is negative, means they must be the same negative. Alright, so now all I need to do is get factors of 12 here, and again there's a lot of possibilities. I won't write them all down here. I think we can all see what's happening if I use 6 and 2 in my last slots here. Let's see, the first product is of course t to the 4th power. The outer and inner product indeed multiply and add up to minus 8t squared, and the last product here is indeed positive 12. So if I ask you to factor this expression, well, after we first put it in standard form, I can then write it as t squared minus 2 times t squared minus 6. And that's the final answer for this problem. Notice I cannot break these down any further. Alright, those remaining two binomials are prime, and you're done when you've factored it into products that cannot be reduced further. Alright, let's get a new screen here. Alright. And they get a little harder still. Let's say I'm asked to factor something like this. Alright, now I get a little antsy when I see a 25 coefficient in my first slot. Well, this sign is positive, which means these signs in between are going to be opposite, plus minus or minus plus. 25y squared. Well, I think I see something happening. If I pick 5 y's in my first slots, and well, 1 is only 1 times 1, there's only one way to break that down, and if I get a minus 10y, let's see, I'm going to have then negative signs in between those two binomial expressions, and I think we've got it. Check it out. 5y times 5y is 25y squared. That's fine. The outer product is minus 5y. The inner product is also minus 5y, and that adds up indeed to minus 10y, and minus 1 times minus 1 is plus 1. So I'd say my final factored form is 5y minus 1 times 5y minus 1. Notice, these binomials are the same, so I can write this in a little more compact form, namely that 25y squared minus 10y plus 1 factors as 5y minus 1 squared. Okay? Another factor. 64 h to the 6th power plus 24 h to the 5th power minus 4 h to the 4th power. Alright, how are we going to handle a situation like this? I mean, this is a degree 6 polynomial. What I can do is greatly simplify this problem if I look for a GCF first. Now the book tells us, the author tells us over and over here, factor out a GCF first. So what I'm going to do first is establish that I've got a GCF of 4h to the 4th power. And hence I can rewrite this expression as 4h to the 4th times 16h squared plus 6h minus 1. Right? So GCF first gives me this somewhat simplified expression. Now we're not done. I've successfully factored out a 4h to the 4th. Now what I'm going to do is see if I can take this trinomial and break that down as a product of two binomials. And I think I see it here. Now I can break down 16h squared in the first slots as 8h times 2h. 1, well, let's see, we've got a last product of -1 here. And I think if I can play my signs right, I can get an outer product of 8h and an inner product of 2h to add up to a positive 6h. Clearly the outer product is going to have to be a plus 8h, the inner product will have to be a minus 2h, and I think we're done. So my final answer, let me rewrite it here without all the diagrams. Will be this expression. Notice, please be sure to carry down your GCF to your final answer, and again be sure to factor it completely. In other words, once you've factored out the GCF, that you can still factor again within the same problem. Okay? On we go. Alright, what are we going to do here? Well, again, the author says, especially in these more complicated problems, look for the GCF first. Okay. Now, what's the GCF of this expression? Well, if I look, there's no variable that's common to all. Alright, so GCF will not involve a variable here. But if I look at the coefficients, clearly I can see a GCF of 5. 5 goes into all of these coefficients evenly. But to make things a little easier, I'm going to factor out a GCF of -5. Remember from the earlier problems in this chapter, you can always factor out a negative value as well as a positive value. I'm going to factor out not a 5 but a -5. I'm going to do that to make my life a little easier when I factor my remaining trinomial. If I factor out a -5, the remaining trinomial inside is going to be 3x squared minus 5xy minus 12y squared. Alright, if you can check yourself, let me rewrite that -5 up here. Alright, please convince yourselves if I factor out a -5 that I'll have this residue polynomial 3x squared minus 5xy minus 12y squared. Alright, now that the GCF is gone, can I factor this again? I think I can. If I put 3x and x in the first slots, now notice, if my last terms involve products of y, well then my inner and outer products will be multiples of x times y. I think I see something happening here. Let's try this. If my first products are 3x squared, the last products here will be 12xy. I'm going to assign the signs now. I think I can play my signs right if I can get 9xy and 4xy to add up to a minus 5xy. I think I'll need a minus 3 here and a plus 4y there. Now let me clean this up a little bit. Can't really fit it all on the same screen. I'm going to rewrite the problem. Factor minus 15x squared plus 25xy plus 60y squared. GCF first. Factor out not a 5 but a minus 5 to give me a positive lead coefficient. That will always make my life easier when it comes to factoring. And then I'll break this down as 3x plus 4y times x minus 3y. Alright. So there is my final completely factored answer. Let me check it. 3x squared, my outer product, minus 9xy plus 4xy is minus 5xy, and minus 4y times minus 3y is minus 12y squared. Alright, so GCF first, and then break it down further. 2 factorings in one problem. Factor completely. Alright. One more I want to talk about before we call it a day. Factor. Again, this kind of represents the upper limit of difficulty in our homework assignment for this section. And let me take some care to write this down correctly. I get 6y cubed plus 13x squared y cubed plus 6x to the 4th y cubed. Alright, what I'll see here is, hopefully you can see them, I'm going to be able to factor out y cubed from each of these terms. What I'm going to do is, because eventually I'm going to be looking at a factored out y cubed monomial, I'm going to rewrite this expression in what the book calls descending powers of x. And that should be clear in a minute. Let me take some care to do that. I'm going to say 6x to the 4th y cubed plus 13x squared y cubed plus 6y cubed. Alright, now I'm going to factor out the GCF. Well, the GCF is, of course, y cubed. I see y cubed common to each of the 3 terms here. Alright, now it should become evident why we wrote our original problem in descending powers of x, because I think I can break this down pretty easily now. This remaining trinomial I'm referring to. Well, my first terms will be multiples of x squared. Well, you want the first product to be 6x to the 4th. I'm going to try 3x squared and 2x squared in the first slots. If both signs are positive here, that means both signs must be positive here. Nice little trick there. And 6. You'll need factors of 6 in the last slots. Now I'm going to try 3 and 2, or 2 and 3 respectively. And again, the real battle here is to get your inner and outer product to add up to the second term you're given. The outer product is 9x squared. The inner product is 4x squared, and indeed those two add up to a 13x squared. So I claim we're done. So I'll get a final return of y cubed times 3x squared plus 2 times 2x squared plus 3. So there is my final response when asked to factor that kind of nasty looking polynomial. So as long as you take it a step at a time, namely look for the GCF first and show good housekeeping skills, hopefully it won't be too bad. Alright, we're at the 30-minute point, so I'll call it a day. This concludes section 5.6, Math 111, Factoring Trinomials.